So if this works, it should be recording the talk. Okay. Actually, what I should really do is I should cover up the camera, because there's really no point to seeing me walking around. Okay. All right, so thank you for coming. It's actually nice to finally meet some of my students. As a professor at a liberal arts college, normally it's not this late into the semester that I am meeting my students. At some R1 schools that I have taught at, I actually meet students later than this part of the semester. So what I want to do is I want to talk about one of my favorite topics, Benford's law of digit bias. Depending on what your interests are, there's a lot of different ways we can go in terms of what we see at the end. I want to try to show some opportunities for student research. So a lot of this is joint work that I've done with students over the years. Some of it is joint work that I've done with a professor of accounting. And a lot of mathematics for me is coming up with good questions to ask. Is frequently we have the same skill sets as other people, but the real difference is, can you come up with a good question to study? And so there's, all the slides will be online. If the technology works, the video will also be online. And then here's just a couple of references. And so the motivating question is, imagine you have a nice data set. And depending on what class you're in, nice will mean very different things. As a pure mathematician by training, for me, Fibonacci numbers would be a wonderful data set. For somebody who's more econ-oriented, maybe stock prices. And a natural question to ask is, what fraction of the first digits would be 1? So this is a very plausible thing, guessing about 10%. And then with a little bit of thought, you said, oh wait, it can't be 10%, and you correct to 11%. So why would you correct to 11%?
Well, because the number 10 starts with 1.
I'm sorry?
The number 10 starts with 1.
Well, the number 10 starts with 1, but the number 20 starts with 2.
Well, the number 100 starts with 1 too.
There's only 9 choices.
Yeah, there's only 9 choices for the first digit. There's only one number whose leading digit is 0, and that's 0. And so that's why we quickly correct from 10% to 11%. But it turns out, a lot of data sets, it's actually around 30% of the numbers with a leading digit of 1, and only about 4.6% start with a 9. Now, I know there's almost 0 chance you'll be bored in this lecture, but maybe in a lecture later today, if you do get bored, start writing down the Fibonacci numbers or something like that, and just doing a little tally and see how reasonable is this. There's a lot of different data sets you can look at and see, are you seeing this bias? So if you look at Fibonacci numbers, Twitter users by number of followers, most common iPhone passcodes, I really don't want to talk about how that data was obtained, distances of stars from Earth. But the Freedom of Information Act is wonderful, not for this, but for other parts of the talk, which I think I have removed from the public version, but happy to talk about in the private version. So you see this preponderance of lower leading digits. And the more different phenomenon you look at, you'll start to notice, well, it's not pure Benford. Some of them are 30%, some of them are maybe 35%, some of them are maybe 26%. As you average more and more different data sets, it becomes more and more Benford. And there's a central limit theorem lurking in the background that can explain a lot of this. So what I want to do today is explain where Benford's law comes from, talk about some examples and applications, sketch some proofs, and if time permits, discuss some open problems. So I know that there's a lot of active undergraduate research that goes on here. We have a program at Williams College as well, where I'm happy to talk about opportunities. Before going into detail, Benford's law is often used to detect fraud, so it's important to just lay down the ground rules as to what we can and cannot do as mathematicians. So a math test indicating fraud is not proof of fraud. Unlikely events can happen. And so I actually emailed Scott Adams and got permission to use this. Your travel expenses are rejected because all of your meal costs are round numbers, you're a liar or worse. And then Dilbert responds, I decided what to order based on what totals to a round number after 15% tip. That's worse. So you have to be careful about why are you seeing something. And there really can be other explanations. A lot of different sequences of numbers or phenomena have this bias. So recurrence relations, which are discrete versions of differential equations, a lot of special functions, iterates of power, exponential rational maps, products of random variables, L functions, my main love. How many of you have seen the 3x plus 1 problem? So maybe I'll talk a little bit about 3x plus 1 later today, and then just lots of other different situations where these arise. So some of the big applications is one is analyzing round-off errors. When you look at how computers manipulate data, is there more likely to be having a rounding error, rounding up or rounding down? Another is determining the optimal way to store numbers. But the biggest is detecting tax and image fraud. If somebody has modified a data set, can you detect it? So if you teach a probability class, it's almost required that you do the following experiment. You split the students into 2 groups, and one group has to flip a fair coin either 100 times or 200 times and record the result. And the other group is supposed to simulate it. And then as the professor, you are supposed to determine which group is which. And if you're not at least 85% accurate, you lose your job. So what do you expect the data would have if you flip a fair coin 200 times? What do you expect to see? Any properties of the data. Again, every sequence of heads and tails is as likely as any other. But that said, there are certain things that you'd be surprised if you didn't see. So any thoughts as to what you would expect to see if you flip a fair coin 200 times? So what are, yes? Yeah, you expect a fairly even split, about 100 heads, 100 tails. And if you know the central limit, then you can actually talk about how far from 100 do you think you can be before it gets too unlikely. And so if you are fraudulently creating a data set, you'll probably make sure you're balanced between heads and tails. What people don't know as well is what is the distribution of the longest run of heads and tails, or the number of alterations between heads and tails. And there's a lot of great results on that. And if you know those, you can very quickly look at the data and say, you don't have a long enough string of heads somewhere. I don't think this data set was naturally generated by flipping a coin. Right. So a little bit about the general theory. So for many data sets, the probability of observing a first digit of d base b, we'll mostly do the base is 10, is the log base b of d plus 1 over d. And so base 10, that's about 30% of the time it's 1. The first thing you should do is you should make sure that this really is a probability distribution. It's non-negative and it sums to 1. It's clearly non-negative, and when we sum them, the sum of the logs is the product, is the log of the product. And so we have the first one is going to be 2 over 1, then 3 over 2, all the way up to 10 over 9. And so when you multiply them all together, you will get it multiplies to 10. You'll have the log of 10 base 10. All right. So just to make sure we're all on the same page, just some background material. How many people here have not taken a class in abstract algebra? Yeah, I actually never took it. I've taught it, but I've never taken it. So you don't really need to take the class, fortunately, for what I need here. I just need some basic clock arithmetic. So if it is 1 o'clock, so let's say it's 1 o'clock now. What time was it 2 hours ago? So if it's 1 o'clock now, what time was it 2 hours ago? 11. So you've just told me 1 minus 2 equals 11. And so on a clock with 12 hours, that's true. And so we'll say 2 numbers are the same if they differ by a multiple of 12. Now for us, what we're really going to do is we're going to care about a clock with just 1 hour going all the way around. And so we care about whether or not 2 numbers have the same fractional part. The next is the significand. If I give you a number, I can write it as some number between 1 and 10 times 10 to a power, where that power is an integer. And then 2 numbers have the same significand, they have the same leading digits. So 2 numbers have the same leading digits if and only if they have the same significand. Because they only differ by padding by zeros. And you can be padding by zeros on the right or the left, depending on whether or not k is positive or negative. And this gives you some idea of the tools that we can use. So if I take the log of my number base 10, I get the log of the significand base 10 plus an integer. I don't care about the integer part, so I can just look at it mod 1, and I'll just get the log of this number, which will be between 0 and 1. Most of the time, you can't just throw away part of a mathematical operation. But since I only care about the log of the significand, I can do this. And so the 2 numbers, if they're the same, if the significants are the same, then that's the same as the logarithms are the same mod 1. And this is going to be the key tool in understanding a lot of stuff on Benford's law. And so for those of you who've done some Fourier analysis or stuff like this, what's really lurking in the background is if I have the function e to the 2 pi iu, which is cosine plus I sine, well, every time I increase u by 1, there's no change because I've gone through a whole period. And so what's nice is I can put in the u or the u mod 1, and I'm going to get the same value there. And that's why this is such a great way to do the analysis, because when I have the logarithm mod 1, I can have the mod 1 or not in the exponential. It's not going to change things. And then I can just have my analysis a little bit easier. All right, so the next concept we need is that of equidistribution, or evenly distributed or uniformly distributed. So we say a sequence is equidistributed mod 1 if it falls evenly in the interval 0, 1. More explicitly, you give me any subinterval AB, maybe it's 0 to 1/2, then half the time I should fall in that. You give me the interval 1/3 to 2/3, then 1/3 of the time I should fall into that. So the fraction of the time you fall into the subinterval AB is just B minus A. So you have to prove at least one thing I'm going to talk. Let's get it over with now. So if beta is irrational, then n beta is equidistributed mod 1. Well, what if beta were not irrational? What if beta was irrational but like 1/5? Then you would get 1/5, 2/5, 3/5, 4/5, 5/5, and 5/5 is the same as 1, which is the same as 0, and then 6/5, which is the same as 1/5. So if beta is rational, you're just going to cycle through values. So there's clearly no chance of having this being equidistributed if beta is rational. Fortunately, if it is irrational, it turns out to be equidistributed. And depending on how irrational it is, and there's a way to quantify how irrational a number is, and that will give you some idea how quickly it sets into being equidistributed.
Just a general question about taking mod 1.
Yes.
I don't know, it's something I've thought about doing, but something I've never seen before, taking mod over a continuous thing. It's like, because in like number theory, you take mod with like the integers.
Right.
What, like, does it still have, like, I know the integers modifying or field, like the integer or like the real is mod 1.
Right.
Do they also form a field?
Well, if you look at the reals mod 1, you're then just going to get the interval 0, 1. And so then you have to just decide how you're defining all of your operations. And so will every element, have an inverse?
Right.
And so you'll still have your additive inverses. You'll still have your multiplicative inverse. The only element that won't be good is going to just be the element 0.
Wait, how are you going to multiplicative? Like, what's the multiplicative?
Oh, I'm sorry. You're right. We're not going to have multiplicative inverses. Sorry. You will just have additive inverses.
If you...
And so we can talk about this afterwards.
Okay.
But in terms of what we're doing here, we just really want to look at things. We just care about the leading digits. I was thinking of the circle. When you look at the reals mod 1, you can also view it as you're living on a circle.
Right.
And I was viewing the angles. And I was doing it as e to the I theta, e to the 2 pi I theta. And there's my multiplicative inverses is because I'm actually doing it in the problem as multiplication, not as addition. And then the inverse of e to the, I theta would be e to the minus I theta. But you're right, you're not going to have both. Now, I'm not going to prove this, that's going to take us too far afield. I'll prove something simpler. That the log of 2 base 10 or the log of the golden mean base 10 is irrational. So let's do the log of 2 base 10. If this were rational, I could write it as 10 to the p over q. Yeah, that's what it would mean for the logarithm to be rational. So I could raise both things to the qth power. So I get 2 to the q is 10 to the p. Well, last time I checked, 10 is 2 times 5. So I get 2 to the q minus p is 5 to the p. I will assume that this is enough to be called a contradiction in this environment, that this is even, this is odd, unless q minus p is 0 and p is 0, in which case we've written this logarithm as 0 over 0, which we're not allowed to do. You can prove that the log of the golden mean is irrational as well. This is a great way to prove different things of Benford, and we'll see in a moment. So let's look at a specific example. So if beta is irrational and beta is supposed to be equidistributed mod 1, I chose one of my favorite irrational numbers, the square root of pi. Does this look like it's equidistributed? What do you think? This is why you need advanced stats classes. Unfortunately, there are people here who teach advanced stats classes. You want to do more than just visual checks. Do you think that this looks equidistributed? You've got 10 data points. It's not, do you expect it to be perfect with 10 data points? No, and in fact, that's why I chose this. I didn't want something that had one element in each bin, because that would look like I'm cooking the books. So I deliberately chose something that was a little bit off, but not terribly off. So almost every bin has exactly one element. One bin has 2, one bin has 0. What should we do to see if it really is equidistributed? Yeah, bump it up. So let's look at the first 100, the first 1,000. If you have really good eyesight, you can see the small fluctuations, but at 10,000, it's looking pretty good. So as I mentioned before, the fundamental equivalence in terms of proving Benford's law is a sequence is Benford if and only if its logarithms are equidistributed mod 1. And the really way to see this is, as we do all the time, we write our number as significant times 10 to the k. We take the logarithm, we look at the logarithm mod 1, and so the logarithm mod 1 is going to give us this number, which is between 0 and 1. So imagine, I write the interval 1 to 10, that's the values of the significant, and then down below I write the values of the logarithm. If I am equidistributed down here, if the logarithm mod 1 is equidistributed, then the fraction of the time I land in here is equal to its length. And that's going to go from the log of 1 base 10 to the log of 2 base 10. Those will be all the numbers who have a first digit of 1. And that's where your 0.3 comes from. Sometimes it's easier to just view the algebra going up rather than going down to the side. And so much of math is just trying to find a good way to look at the algebra. And so if I'm equidistributed on this side, then I'm here about 30% of the time, which means I'll have a leading digit of 1 about 30% of the time. Any Rubik's Cubes people here? So I love doing stuff with Rubik's Cube. So this is one of my favorite ways to emphasize the algebra. And so let's see if we can actually pull this one. Yes. Oh, got twisted a bit. Well, I don't know. It got mixed up in the drive here, which is fascinating. I can still do with this. All right. I'll solve it later. So here is a Rubik's Cube. It's this one over here. And if you look at the green side doesn't turn the way you would expect a normal side to. This is really the same as a regular Rubik's Cube. You have to hold it at a 45-degree angle. And then here is the front face. And then here are the two sides. And so if you look at the algebra the right way, it's something you already know how to do. What's really going on with Benford's law, this digit bias, there really is no digit bias. But in order to get rid of the digit bias, you have to look at the logarithm of the number modulo 1. For most things, that makes absolutely no sense. What's the temperature today? Well, you don't really want to know the temperature by taking the logarithm. What someone's batting at, So there's natural values to the numbers. But if you do a transformation like this, the bias disappears. So let's look at powers of 2. So the log of 2 is irrational. So if I look at 2 to the n, when I take the logarithm, I get n, the log of 2 base 10. So that should be Benford. Fibonacci numbers of Benford, and that's using the golden mean. So if I look at an plus 1 is an plus an minus 1. How many of you have seen solving recurrence relations like this? This is one of my favorite methods of mathematics. This is the method of divine inspiration. You write down the answer and you show that it works, and therefore you must be correct. If you think about the Fibonacci numbers are growing. An plus 1 is going to be at least twice an minus 1. Right? And it's going to be less than twice an. So both of these give you something that's growing exponentially fast. So it's not unreasonable to guess that the Fibonacci's maybe grow exponentially fast. So guess an is r to the n. This is fun to say as a Bostonian. So you get r to the n plus 1 is r to the n plus r to the n minus 1. You get r squared is r plus 1. Well, that's quadratic, we can solve. You get 2 roots. And then the general solution, because it's linear, is just c1 times the first root to the n plus c2 times the second root to the n. So if you plug this in, you'll see that it works. And so this is one of my favorite formulas in all of mathematics. It's Benet's formula. And the way I like to describe it is, imagine a number beats you up and there's a police lineup and you're trying to figure out who it was, and they ask you to identify the number that did this to you. That's the integer that did this to me. When you look at this, you've got division by 2, you've got square roots. This does not look like an integer, but it is always going to be an integer. Now what's amazing is this number here is greater than 1 in absolute value. This number is less than 1 in absolute value. So when n gets very, very large, this number is so close to 0, it doesn't really matter that much. And the nth Fibonacci number is approximately this. And that's why the Fibonacci numbers are Benford. You have to do a little bit of bookkeeping to show, because, well, what if my number is, 1 billion? Then a very small amount there could change me from having a first digit of 1 to having a first digit of 9. So you just have to show that that doesn't happen too often. So most linear recurrences are Benford. So if I give you an plus 1 is twice an, you can prove that that's Benford. Not everything, though, is Benford. If I give you 2an minus 1, if I take a0 equals a1 equals 1, then I get 2 minus 1 is 1, and I just get 1 for all eternity. If I take a0 equals 0 and a1 equals 1, then I get an is equal to n. So it's not always going to be Benford, and you can quantify when it's not going to be Benford. All right. So let's look a little bit at some data from powers of 2. So we had some discussion earlier about whether or not the data was good when we looked at the square root of pi. So here is the digits. Here's the observed numbers, the observed probabilities, the Benford probabilities. I'm looking at the first 60 values of 2 to the n. I'm only listing the first 30 over here because the numbers are getting large. And I have a finite amount of board space. Do you think the data looks good for Benford, or do you think there's some concerns? You look like you have a concern. Any digits where you have some concerns about how good the fit is? Yeah, 9 doesn't look so good. I thank you for saying 9 because that was the one that was highlighted. Well, one of the things you learn is the observed probability is actually pretty small, so we really shouldn't have that many occurrences. So maybe we should be binning a couple of these together and playing some games. Any computer science people here? How many megabytes are in a gigabyte?
How many megabytes in a gigabyte?
Yes.
Well, I'm actually not, it's like 1,000 I thought, we've also put like 1024.
Yes, it depends on whether or not people show the proper respect to the classical prefixes. Right? If you show the proper respect, how many megabytes should be in a gigabyte? Just using the prefixes, it should be 1,000. Why do computer scientists often do 1,024? Powers of 2. So 2 to the 10 is 1,024, is almost 10 cubed. Imagine you were in an alternate reality where 2 to the 10 actually equaled 10 cubed. Then every time you increase n by 10, you actually return to where you started with 3 zeros padded. And that's why, if you look over here, it's almost 3 zeros padded. It's almost 3 zeros padded. And it's going to be a while before you start to see a 7 occur. Or a 9. In the limit, you will have the right frequency, but it will take a while for that to come in. So I chose 3 of the top constants in all of mathematics: gamma, e, and pi. And so what I did is I looked to see how good of a fit Benford's law was for them. And so I did a chi-squared test. So if you haven't seen chi-squared tests before, the smaller the number, the better the fit. And if it's a good fit, then I should have low values. When you look at this, which numbers look to be pretty good? Gamma and e. And pi is terrible. 95% of the time, I should get a value of 15.5 or less. The other ones are almost 0. But pi is getting small, mostly getting small, and then it gets larger again. What's going on? So who can rattle off digits of pi? There's going to be at least somebody who can. Okay, how many digits? Okay, great, excellent. Is there anybody who can do more than 80? You get the next one and you win. How many digits of pi squared can you rattle off? You stopped at pi? Pi cubed, pi to the 4th. Oh. So here's the plot of the log of chi-squared for powers of pi and powers of e. Now you can see that the chi-squared values for e are pretty small. And because things are fluctuating on such a large scale, I'm actually plotting the log of the chi-squared values because I've got to go from 46.65 down to almost 0. What do you notice about what's going on for the chi-squared values of powers of pi? What do you see from the data? And it doesn't have to be perfect, but do you see any patterns? What do you mean by recursive?
If you plot like certain points like logs, like some number.
Good. So I would use periodic rather than recursive, but it does look like it has some kind of repeating structure. And if you look, the actual shape looks pretty similar. Anybody want to guess as to what the period is, approximately?
Wait,
I'm sorry? So what would you guess for the period? 175. Here's 200. It goes to its lowest point before that. 175 is not bad. Do you want to go up to 180? Do you want to go down to 170?
I'll go down to 170.
You go down to 170.
Yeah.
So you think somewhere between 170 and 100, here's probably 100 is here. Here's 150. 175 is not a bad guess. Now I had mentioned powers of pi. Trying to get you away from 175, but pi to the 175, if you had really learned your tables when you were younger, is 1.0028 times 10 to the 87. So every time you increase by 175, you almost return to where you started, but padded by 87 zeros. And so one of the things the IRS cares about when they look for tax fraud is how quickly should behavior set in? How much data do you need before you can be confident that something nefarious is going on? And for problems like this, a lot of it is related, I'm not going to go into details here, about how irrational a number is. All right, I'm going to skip the next slides. I'm going to just display them so that they're actually being recorded. This is work my students did 2 summers ago, generalizing some results on recurrence relations. All right, so I want to talk a little bit about Benford's law. How many of you have seen a proof of the central limit theorem? Okay. So imagine you have a long street and the houses are numbered 1, 2, 3, all the way up to L. It's very boring. If L stops at 199, you just had a whole string of houses with the first digit of 1. Whereas if it stops at 999, you have a whole string of numbers that are not a 1. So the probability of having a first digit 1 is going to fluctuate between 1/9 and 5/9. And so here's a little plot of how things look. If you take logarithms, it looks much nicer, much more periodic in terms of what's going on. So let's modify the street problem a little bit. What if we have many streets of different lengths? And there's a lot of ways to do this. And the more random something is, the general rule is the more Benford it becomes. So here's the first. We're going to take 1,000 streets, and they all have houses from 1 to 10,000. And so it's not going to be Benford at all. Imagine now we have 1,000 streets, and the length of each street is a random number from 1 to 10,000. And in that case, the first digit and the first 2 digits look a lot closer to Benford. Rather than rinse, repeat. Take a random number from 1 to 10,000, then take a random number from 1 to whatever that was. And you can see the fit is getting much better to Benford. You can do it one more time, it's getting really good. And so just basics of probability. So we say X is a random variable with density P if the following is true. P is non-negative, it integrates to 1, and then the probability you take on a value between A and B is just the area under the curve from A to B. So the mean is the average value of the integral of X times P, the variance is how spread out things are, and then independence is knowledge of one random variable typically gives you no information of another. So, the most important probability distribution is frequently the normal, the bell curve, the Gaussian. When you have this many names, it's important. E to the minus x minus mu squared over 2 sigma squared divided by 2 pi sigma squared, so it integrates to 1. And the central limit theorem is if you take a bunch of independent, identically distributed random variables and you look at their sum, well, if each one of these is on average mu, then I should subtract n times mu, so I have something that has mean 0. And then by dividing by sigma square root of n, I get something that has standard deviation 1. I'm basically normalizing to talk about apples and apples. And so the central limit theorem says that this will converge to the standard normal as long as my random variables are nice. So let's do a test. And again, this is why you need more, this is why you need advanced statistics, so you're not just doing these visual tests. Does this look like a good fit? So what I'm doing now is I'm taking a uniform distribution on minus a half, and I'm comparing it to the standard normal. It's not great, it's not terrible, but it doesn't look that Gaussian to me. If I do the sum of two uniforms, so imagine you throw two fair die. If you throw two fair die, you get numbers from 2 to 12. You get the number 7 1/6 of the time, and you get 2 and 12, each 1/12 of the time, 1/36 of the time. Is that a good approximation to the bell curve? It's not bad. If I do it 4 times, it's really good. If I do it 8 times, it's even better. And so your Mathematica can churn out explicitly what the closed form density is for the sum of 4 uniform random variables. I think Mathematica told me no when I asked it to do 8. But this is enough to illustrate the point. You do not want to work with this. I know I don't. And the whole idea is we want to bypass having to work with stuff like this to appeal to the central limit theorem. Let's work with something nice and then just control the errors, control how far apart things are. So what I'm doing now is I'm looking at a normal random variable, mean 0 variance sigma squared, and I'm looking at it mod 1. Because we saw for Benford that it's mod 1 that really matters. And so when we look at it mod 1, I'm choosing the variance as 0.01. So if the variance is 0.01, the standard deviation is 0.1. That means most of your probability is going between 0 to 0.1 or 0.2, and then maybe -0.1, -0.2. And if you look at the plot here, you can see most of my probability is within 2 standard deviations of 0 when I'm looking at it at mod 1. So this is the Gaussian with a variance of 0.01. If the variance is 0.1, look at how close the Gaussian is to the uniform. Is that a good fit to the uniform? No, but it's not bad. If I make the variance 0.5, is this a good fit to the uniform? Yes, because you have to look carefully at the y-axis, right? Look at the labels. It's going from 0.9999 to 1.0001. Any XKCD fans here? So one of my favorite XKCD fans is, two people are in a relationship and one goes to the other and says, I think we should break up, and they present their evidence. And the person looks at their plot and goes, I agree with you. And the party says, I knew the data would convince you. No. I can do better than somebody who doesn't label their axes. You always want to look and see what are your axes. And so over here, I'm trying to fool you into thinking that it's not a good fit. There's almost no variation here at all. So whenever you see a product, take a logarithm. So imagine I have a product of independent random variables. So if I take a logarithm, then the log of a product is the sum of the logarithms. By the central limit theorem, if these are nice, these will converge to being normally distributed. And so if they are normally distributed, they're going to be normally distributed with a growing variance. And what I was just trying to show you a moment ago is if you take a normal with growing variance and you look at it mod 1, it becomes a uniform. And there's your Benford's law. All right, so applications. Anybody know who the Steve Miller is on the right? He used to work in the IRS department, and he got into trouble for using politics rather than mathematics to do some of his job. And so here's one of my favorite applications. So an audit of a bank, you get a huge spike of numbers starting with 48 and 49, mostly due to one person. And what was happening is the bank had a policy that if somebody reported their credit card stolen, they wouldn't bother investigating if the amount was too little. It's not worth the time to find, who stole it. What was the floor? $5,000. Anything below $5,000, just write it off. Anything above $5,000, investigate. And so a person was having their friends get credit cards, run up debts of just below $5,000. Your card was stolen. Oh, that's so terrible. Don't worry. You're not liable for any of the charges. So, the question then becomes, if you know that the bank is doing this, how do you adjust what you're doing? The simple solution is no one should ever be safe from an investigation. Every now and then you should investigate a credit card with your $13.17. Can anybody see the cat hidden in the tree? So one of the big applications of Benford's law is image fraud. So I'm going to give you a quick understanding of how I view image transmission. So you often have your red, your green, and your blue pixels. And each one you have a number from, say, 0 to 255. And so that gives us over 16 million different colors we can send. For me, 16 was probably enough, but this allows you to have a tremendous number of shades. So steganography is the art of hiding a message in another message. So take one of the colors red. And so we write our numbers in binary. So it's going to be a number from 0 to 255. So if we just change the last digit, it's not going to change the amount of redness by much. Even if we change the last 2 digits, it's not going to change it by much. What you can do is you can take a low-res image and hide it in a higher-res image. So when I said that there was a cat in the tree, the cat is actually the entire size of this image. And so one of the applications of Benford's law is to detect, has somebody modified an image? If you want to just write a message, say black letters on a white piece of paper, that's really easy to hide in a message like this. If all you do is just change the last digit, you're going to be caught doing that, so you want to do something a little bit more interesting. All right, so in terms of, I'm going to skip a lot of the Benford good stuff and go to, we'll skip the zeta function. I'll go to the 3x plus 1 problem, because I know some people have heard of this. So who here has not heard of the 3x plus 1 problem? Okay, it was, my two favorite quotes is Kakutani described it as a Soviet conspiracy to slow down American mathematics because of how much time was spent unproductively on this. The great Paul Erdős said mathematics is not yet ready for problems like this. And so the idea is take any odd number, multiply by 3 and add 1, and then remove as many powers of 2 as you can. And then lather, rinse, repeat, keep doing this. And the conjecture is no matter what positive integer you start with, you will always end up at 1. If you don't believe me and you want to challenge, what number should you take? 27. So 27 is significantly more painful than all the other numbers near it. And so for instance, let's take the number 7. 7 is odd, so I multiply by 3, add 1, 22, divide by 2, get to 11. And you keep going like this, and eventually you get down to 1. And once you're at 1, you will always stay at 1. So the number I'm putting down here is recording how many powers of 2 I've removed. And so if I look at the 2 path, it's just the first 2 things I did. The 5 path would be looking at the first 5. The M path would be looking at the first M. It turns out that these behave like independent, identically distributed geometric random variables. And so you can use a lot of good probability to analyze this, and you can prove Benfordness. So the first paper in the subject was by myself and a mentee of mine, Alex Kontorovich, who has now greatly surpassed me. And we proved not what you want to prove, but what we were able to prove. So we looked at the mth iterate, and we divided by where we expected to be after m tries. And we proved that that went to Benford. That's not what you want to do, but we were able to do that. I gave a talk on this at Michigan, and Jeff Ligarius and Soundarajan then extended this, and they proved what you would want to do. As I said, for almost all starting seeds, you are within a certain tolerance of Benford. And so you can prove Benfordness. There's a lot of really good math that goes behind this. A lot of this comes into how irrational are certain numbers. So just giving some data, this is looking at a 10,000 digit number. These are very easy to do on the computer because all we're doing is we're multiplying by 3, adding 1, dividing by 2. You can just view your number as a string. And you can see the observed and the predicted probabilities are terrific. Actually, I believe I have about 5 minutes left. So what I want to end with is a little bit on stick decompositions. And so this is joint math and physics. One of the professors who was mentoring this with me is actually a colleague of mine, professor of physics at Williams. And so consider a stick of length L. And then what we want to do is we'll uniformly choose a probability P, a proportion between 0 and 1. And we're going to split the stick into two parts. One part will be length P times L, and the other part will be 1 minus P times L. And then again, lather, rinse, repeat. Each of these sticks split up. And what we could do is we could split each one always with the same probability. So this will give us a p squared L, a p1 minus pl, a p1 minus pl, and then a 1 minus p squared L. Or at each stage, you could keep choosing new probabilities. You can do either one. In the interest of time, I'm going to just fix one probability p and keep splitting. And so here's what you have after 2 stages. And you can ask, do you expect there to be a Benford's law? Are there any probabilities that you think might not be Benford? What would be a bad choice of P? 0 is bad because you're not splitting anything. So if 0 is bad, 1 is also bad. And there's one other choice that should just immediately strike you as bad. 0.5, because then every piece will have the same length. So the conjecture was, as long as you don't choose p equals a half, you will always get Benford. And so here's choosing p equals 0.51, here's choosing p equals 0.99, and you can see it looks pretty Benford. Counterexample, if you choose p equals 1/11th, it is not Benford. And so I've got just a few moments left, and that's enough time to just show the proof. So imagine you're at the nth level, so you have 2 to the n sticks. You have n plus 1 distinct lengths. So I can write the lengths as p to the n minus j times 1 minus p to the j. And different lengths will occur at different frequencies. The length p to the n occurs only once. The length 1 minus p to the n occurs only once. And in fact, the number of times this occurs is just the binomial coefficient n choose j. And so what's nice about this is, again, go back to the Rubik's Cube that I showed you. It's all about viewing the algebra the right way. Instead of writing it as p to the n minus j times 1 minus p to the j, pull out the p to the n, and then put the j down, the p to the j down below, so I have 1 minus p to the j. And when you look at it like that, to go from one length to the next, you just multiply by the same constant number, 1 minus p over p. If 1 minus p over p equals 10, it's not going to be Benford. If 1 minus p over p equals 100, it's not going to be Benford. If it's 1/10, it's not going to be Benford. If 1 minus p over p is the square root of 10, then if you do it twice, that's the same as multiplying by 10. So it all comes down to, is this equal to 10 to a rational power? So if 1 minus p over p is 10 to the y, it's not going to be Benford. Otherwise, it will be Benford. The only thing that makes this a little bit challenging is not every length occurs the same number of times. And so there was some talk earlier about repetition and looking at things modulo. If I look at all of the indices j mod q, they will have the same leading probability. And you can just basically go through and show that if I just look at all things in these arithmetic progressions, 1, q plus 1, 2q, 1 plus 2q, 1 plus 3q, I'll stop there. That's going to be essentially the same probabilities as 2, 2 plus q, 2 plus 3q, and so on and so on and so on. The shift in probability is going to be negligible. And so you can just go through and do the paperwork, the detailed calculations at the end. So if I take p equals 3/11ths and do 1,000 levels, well, I'll get the log base 10 of 8/3, that's irrational. And I expect to see Benford, and it looks pretty close to Benford. If I take p equals 1/11th, then 1 minus p over p, that's going to be a nice rational power of 10, and not surprisingly, it looks very non-Benford. So if you calculate 1 minus p, in fact, we're just getting one value every single time. Another interesting one is 1 plus 10 to the 33 over 10. I'm sure there was a reason why we chose 33 over 10. That is sadly now lost in the years that have followed. Just mentioning it very briefly, you can play games where you choose different random variables at each time. The analysis becomes a lot harder than if you have the same random variable every single time. And what you basically do is you form a family tree. And you have to codify how closely related are you to your neighbors. So these two people are extremely well related, whereas this one and this one would be very distant cousins. And so you just need to quantify how close you are to the various ones. So just to quickly conclude, we have seen many different systems exhibit Benford behavior. The key ingredient in the proofs is logarithms and equidistribution. And then to really get into the nuts and bolts, it's Fourier analysis. It's looking at sines and cosines, because when you look at the exponential function, it's wonderful with respect to the logarithm. Most of the time, if you want to evaluate f at x and f of x mod 1, you're going to get very different answers. But with the exponential function, we can drop off the integer part without any real harm. And then there's a lot of applications of this. So I actually gave a talk at this at the Boston headquarters of the Internal Revenue Service. A very, very interesting place to talk mathematics. And they are quite concerned. And so what they can do is they know that people cheat on their taxes. But individuals do not have necessarily enough data points for them to be able to say that you yourself have cheated. Anybody want to hazard a guess? I know it's not something you would do, a category that people might cheat on their individual taxes. Tax credits, in what sense?
Something like preparing more tax list and they actually have like.
The big one is charitable deduction. And this is why the IRS is now requiring a lot more detail in terms of, so how much was those clothings or those things that you donated really worth? And so with a lot of data points, you can actually see some things. All right, so thank you.